Have you ever wondered, are we really alone? Is Earth really that special that it's the only place in the universe that has life?
An explorer is about to land on Mars, looking for answers. A make-or-break moment for a very expensive robot.
This seems crazy. Why again does this work?
If it doesn't work, it's kind of a bad day on Mars.
I don't give a damn what requirements we wrote down.
That pressure is really intense.
Tonight, behind the scenes, building the new Martian mega rover. Our best chance yet to uncover the story of life on Mars.
This mission is not going to be easy. It hasn't been easy. But we want an answer, and we're going to go get it.
Back in 2006, we were called to NASA headquarters. The event involves a whole bunch of top brass, including the NASA administrator. The room is full. The other centers are all live. Everyone's milling about nervously.
Adam Stelzner, an engineer from NASA's Jet Propulsion Lab, has some explaining to do. In 2004, his team landed twin rovers on Mars inside airbag cocoons. But they have something radically different in mind for landing the next mission. A much bigger, more powerful rover they call MSL, Mars Science Laboratory.
And I had to present this arguably crazy-looking plan to land this huge rover on the surface of Mars. So it was a little scary. So Martian entry, descent, and landing. It's about energy control. It's got 4 basic components, and that goes for any Mars EDL.
This is the most dangerous phase of any mission to Mars. Arriving at 21,000 kilometers an hour, and on the ground just minutes later, with no help from anyone on Earth. They call it 7 minutes of terror.
.99% of the velocity comes out in the entry phase, where we dissipate the energy to the Martian atmosphere.
It all happens faster than the time it takes to send one radio command from Earth. So every step is pre-programmed.
The parachute slows us down from 1,000 meters a second to about 100 meters a second.
So far, it looks a lot like any other Mars landing. But now, things take a strange twist.
Go into a powered descent mode. We descend for the last 2 kilometers, look at the ground with the radar, and then about 20 meters from the surface, we employ our touchdown system, which is called the Sky Crane. We deploy the rover. We are still maintaining a constant vertical velocity. We touch down, cut the rover free, and fly off. It is a new architecture, and frankly, it looks crazy. It looked weird. It looked scary. Very crazy, wacky thing. And it looked like that to the folks at NASA headquarters. And so we went through what ended up being close to 2 hours. There's lots of questions, there's probing.
They ask about the airbags that worked so well last time. But this rover is 5 times heavier. Airbags would have to be impossibly huge. so that's out.
Very low velocity.
What about a traditional lander with legs?
Legged landers, a la Viking.
With a heavy payload, it would be unstable, especially if it happened to land on a slope.
And that's one of the reasons that we don't like it.
The Sky Crane, though, can drop the rover anywhere it can drive.
It utilizes the rover's inherent terrain hugging capability. And the rover is placed in a condition ready to rove.
By the end of the day, the head of NASA was convinced.
He says, well, you know what? I came in here thinking that this was the craziest thing that I'd ever heard of, and I still think it's crazy. But I think it might just be crazy enough to work.
No one has ever accused the folks at JPL of lacking confidence. But after the rover's Spirit and Opportunity landed on Mars, the confidence and ambitions went through the roof.
Oh, yes. You had a set of engineers and wide-eyed scientists who had just scored the greatest success of their lives. And there was a group adrenaline rush throughout the entire Martian community, which was almost like we can do anything.
Spirit and Opportunity were expected to last a few months and do basic geology. Next time out, they wanted an upgrade. A mega rover called Curiosity, built to last years and do things on Mars that had never been done before. Curiosity would trek 20 kilometers or more through the rugged Martian outback, capturing everything in high-definition 3D. This would be rocket science on steroids. A fully loaded rover with a nuclear power supply and a dream payload of scientific instruments.
The scientists say, what can we do next? Can you possibly? Yes, we can do that. And could you possibly do this? Yes. And this man wants to fire a laser at a rock and plasmatize it and determine what it's made out of. Oh, yes, we can do that too. And everybody was just carried along on a giant tsunami of confidence and passion and enthusiasm.
Most of all, they wanted to tackle the big unanswered question about Mars. Was it ever a place where life could exist? For that, they would need an organic chemistry lab inside the rover. And that's what they got.
It's going to carry with it an entire laboratory. We've never done anything like that before. We've sent a few instruments, but we haven't sent an entire laboratory. We're going to see Mars in a whole nother way because we have this package of tools to look at it in a completely different way.
Mars is a brutally cold, dry, almost airless world, bathed in lethal radiation. Not good prospects for life. But it wasn't always this way. When Mars was young, there was water. It was the same era when life first took hold on Earth. Could it have happened on Mars too? Or perhaps first?
It is just possible that whatever life really is began there and was knocked off the surface and then rode on a rock from Mars to the Earth. Understanding those early days on Mars will help us to understand where we came from.
Have you ever wondered, are we really alone? Is Earth really that special that it's the only place in the universe that has life? We're finally going to get to go find out.
Water clearances.
This is the biggest spacecraft we've ever built. Everything is supersized. It comes with all of the pleasures and pitfalls of something that big. We have a new landing system because of the size of the vehicle. We've got an instrument package that's much more complex. It makes everything more complicated.
It all has to be ready for launch in September 2009, a year and a half away. As they orbit the Sun, Mars and Earth line up once every 26 months. That's when missions can be launched. Miss that chance, and the next one is another 26 months away. A delay that would cost millions.
I'm used to high-pressure schedules, but we have a lot to do. People think that this might be easier than it is. It's not. It's very hard.
They're building 2 rovers at the same time. The one that will go to Mars, and an identical twin for hard testing on Earth.
It has to work reliably 100 million miles away from us, and so before we send it, we test the bejesus out of it.
We're going to fire in our flight-like timeline. Rules of engagement, everybody has to stay in the tent, and everybody in here has to have safety glasses on. If there is an emergency, we're just going to...
Today, they'll simulate a key event in the landing sequence. The violent jolt when the rover's mobility system drops into place.
We're going to do our final countdown, and then we'll test.
The wheels are off to reduce weight, simulating Mars gravity, less than half what it is on Earth. But it still has to survive a big shock.
Verify everyone is in a safe location. 3, 2, 1, fire.
No damage, but they're starting to wonder if they've created a monster.
So there it is, and this just beast is sort of jostling around. We were asking ourselves, what have we done?
That's the situation we found ourselves in. You take something that you think you understand, and you say, let's do it bigger. Let's not make it twice as big, let's make it 5, 10 times as big. Now you get to a whole new realm of complexity that we had never faced before.
Next week, we are doing some parachute tests up at Ames, at the full-scale wind tunnel up there for the MSL supersonic parachute.
One of the most difficult things to do is to test the strength of the parachute. The only way to do that is to actually inflate it. Since we have a very large spacecraft, we need a really, really, really big parachute. We had to go to the world's largest wind tunnel in order to accommodate this big of a parachute.
Okay, pass on 50 knots, test section. Do you copy?
You spend a lot of time talking about stuff and analyzing things, and the test is sort of a cold, hard truth waiting for you at the end of that. So there's a little bit of anxiety as you get ready to go.
It's almost showtime. We're almost to the point where we're ready to start the tunnel right now. So.
The chute opens at 1,500 kilometers an hour on Mars. On Earth, where the atmosphere is 100 times denser, they can generate the same force at about 150 kilometers an hour.
Armed. 3, 2, 1, fire. Good shoot. It was too easy. It was too easy.
The problem is, parachute testing is never without its surprises.
Passing 50 knots in the test section.
The next day, test number 2, the same kind of chute at a higher speed.
On my mark. 3, 2, 1. Bad shoot. Oh.
We really had no idea what was going on here. It was just a total tangled mess. I mean, it was frightening. What if this happened on Mars? The spacecraft tumbling to the ground with this parachute flop in the back.
It was busted up pretty good. Lots of little pieces.
Smaller versions of this parachute have been tested and flown on Mars many times before. They never did this. But a smaller parachute is not an option. If a big chute won't work, the mission is in trouble.
I have nobody to blame but myself. All of us who sort of formulated this are like, you know, we're not saving somebody else's game, we're living our own. So, it's freaky, scary. It's on the line. How'd it look?
Get the freak out of here. We may have live ordnance. Get out!
We really didn't know what was going on. And it scared the heck out of us because we'd never seen this type of failure before.
Let's say you did that. I don't have a solution to the problem yet.
We were truly baffled. And so we spent months trying to figure out what had happened, why it happened, doing all the failure scenarios, really to no avail.
Was it Eric or Keith? And we went through a lot of technical soul searching. We were asking ourselves, have we run into a real big, sort of a showstopper problem here?
Definitely failed on that one side first. Very asymmetric opening.
The problem is we didn't have enough data. So for the next test series, we just packed the wind tunnel full of cameras.
This is control room. You guys ready for the high-speed cameras?
We're ready to go.
I would venture to say it was one of the most photographed parachute inflations in history.
3, 2, 1, fire.
So we shot it out, hoping, you know, okay, we'll get another failure, we'll see it, we'll diagnose it, and we'll fix it. Problem was, it opened up beautifully. And so, again, we were kind of stuck.
I don't see anything. No, it doesn't mean we can't find anything, but on first inspection of this, I didn't see anything.
They keep trying, and one chute after another opens perfectly. But they still need to catch a failure on camera to understand why it happened and rule out the possibility that it could happen again on Mars. 15 months before launch, they're on their third set of chutes and running out of time.
4, 3, 2, 1.
Yeah, baby.
That's it, buddy. Adam, please try to stand by their goal to
That's what we need.
Cool.
You see this, Keith?
In the slow motion footage, they can finally see what happened.
Oh, we got it all.
Yeah, we got
it all.
When you open the parachute, it's like a sort of a collapsed bag. And sometimes the front edges of the bag overlap before it starts to fill and start to turn the parachute inside out.
It's right there. You get a little piece of fabric which has pulled itself on the wrong side of where you're supposed to go. It inflates and it starts to pull the parachute through.
And unfortunately, it starts to tear itself apart. It rips to shreds in the wind tunnel.
The problem is not the size of the parachute, but the amount of time it takes to open in the wind tunnel. With the air moving at 150 kilometers an hour, the MSL chute takes 10 times longer to inflate than it will at 1,500 kilometers an hour on Mars.
On Mars, we're vulnerable for less than 1/10 of a second. They just don't have time to misbehave.
We concluded that the phenomena that we see at Earth is not going to happen at Mars. Earth and Mars are different. We can never test a parachute exactly as we'd like to. And that anxiety will be plaguing me on landing day. There will always be this residual nagging risk that some difference could be our downfall.
It's not enough for Curiosity to land safely on Mars. It also has to land in the right place.
We're looking for habitability. A habitable place has the stuff that life needs. It doesn't mean that life is there. It just means that everything that life would need is there.
It means water. It means a source of energy for microorganisms to live, and it means availability of carbon, which is the building block of all life as we know it.
We know there was once water on Mars. We know there's energy from sunlight. So far, we haven't found the carbon. But we've never looked with tools as powerful as the ones Curiosity will carry. The heart of the rover is a miniature suite of laboratories called SAM, Sample Analysis at Mars. SAM can detect organic carbon. And if that carbon were ever part of a living thing, it would have a telltale signature like a fossil.
We're used to thinking about fossils in a large sense, dinosaur bones. Microorganisms don't have bones, but they do have other organic materials they can leave behind. It ends up in the rocks, in sediments, and it becomes a molecular fossil. That's something that SAM can detect.
With the Mars Reconnaissance Orbiter, the team searches for minerals that formed when Mars was wet and may have organics trapped inside. This ancient river delta is one possibility.
This looks so Earth-like. These patterns that you see here are identical to deltas that form on Earth, where a river comes into a body of standing water and then drops its sediment. Turns out these are the kind of places where organic carbon loves to accumulate. If life had been present on Mars, this is a place where you'd have a pretty good chance of going to see it.
They have to choose their site 6 months before launch, and there are lots of options. Ancient rocks from the earliest days of Mars, when life may have first taken hold. Basins where pooling water left layers of sediment behind. A crater with a mountain in the middle that may once have been an island in a lake. The best sites for science almost all have rugged terrain that exposes geological history. These places were out of reach in the past because the landers needed smooth, flat ground, and the smallest target they could hit reliably was 80 kilometers long. The problem was predicting the density of the atmosphere on landing day.
Is the atmosphere hotter or colder than we expect? Is it windier or less windy? Is it dustier or less dusty? A little lower density, and you're going further. A little greater density, and you're going shorter. That spreads out a large footprint on the surface of Mars.
This time, things will be different. During entry, the spacecraft will drop 150 kilograms of ballast, making it tilt forward. That generates lift, like an airplane wing, so it can fly higher or lower as needed to stay on target.
The spacecraft measures the resistance it's experiencing from the atmosphere. And if that resistance is too much, it goes higher. If it's too little, it goes deeper. And so it's always trying to make that resistance what we had thought when we planned out the trajectory to our landing site.
Instead of an 80-kilometer landing strip, they can hit a spot just 24 kilometers long, putting dozens of new places in reach for the first time.
We can't do them all. So now we've got this high-class problem of all these great sites, but yet we've got to pick just one of them.
The engineers have their own problems. With 10 science instruments and 33 electric motors, the rover has a huge appetite for power. Its nuclear generator will convert heat from plutonium into 110 watts of electricity.
It provides a very reliable amount of power for years, decades. But 110 watts, like a 100-watt light bulb, is not a lot of power.
They'll have to charge batteries at night, stockpiling power to use during the day. But Martian nights are cold, 75 degrees or more below zero. By morning, the lubrication in the motors, called actuators, will be frozen stiff. They'll have to spend some of their stored power to heat them up before they can do any work.
Now, we thought that we could build actuators that didn't need to be heated. And that's technology with titanium gears and dry lube. Not liquid lubrication, but dry lubrication. And when we built them up and tried them out, they were great. The one thing we didn't do in time was a life test, where you just ran it and ran it and ran it and see whether or not those motors would last for 2 Mars years of driving.
We're at 12,486 RPM.
So about right, we're in the middle of a life test and something doesn't look right. Okay, well, let's do a health check. And during that health check, you hear, and you're like, oh no. And then you pull it apart and there's dust everywhere and the gearbox is eating itself up and you're thinking, oh, I don't know what to do. I don't, you know, who do you tell? I mean, what's your first phone call? You know, it's like.
The combination of the lubrication and the titanium gears and the whole design, it just wasn't going to work.
They have to start over from scratch with a new design, a major blow to the schedule and budget.
That pressure is really intense. If you're not able to deliver, we don't have a mission.
The Mars Science Laboratory is in trouble. But it's not the radical sky crane landing system that's causing problems.
Up slow.
With the electric motors sent back to the drawing board, the rover is just a box full of wires. There's no drive system, no robotic arm or camera mast, no moving parts at all. All that has to wait for the new motors, while the countdown to launch continues.
You really start to feel the pressure, you know. Mars is coming, Mars is coming, Mars is coming, and that, you know, your launch date is set.
The celestial clock never stops ticking. 10 months to launch, and if they miss it, the next chance is another 26 months away. The motors aren't the only problem. The rover electronics and computer systems are all new and unproven. The software for everything from landing to rover operations on the ground is running more than 2 million lines of original code.
It's gotten very complex, and it's taken us more time to test than we thought. As you might expect, when you look at it and all the things it has to do, it's out there. It's tough.
It's a difficult decision. Spend more money now in an all-out effort to make launch in 2009, or delay 2 years at even greater cost.
You can always dump more money into things. The question is, will that money have the intended effect? And once you put the whole system together, do you have time to really test it and build your own confidence that it will be a successful mission?
They decide to stay on track for 2009 and push hard to finish the rest of the spacecraft while the rover catches up.
Try to do it at the same time because we got 2 teams who are doing it.
So we've got guys coming in at 4 in the morning, working till 11 in the morning, coming in at midnight, working till 4. I mean, it's full court press right now.
We were really on schedule to make it. Working 24 hours a day, 7 days a week, turning out actuators, making sure that everything tested, flight ready, ready to go.
Then, a new problem crops up. Something is binding inside one motor. It's fixable, but it means they all have to be taken apart, inspected, put back together, and retested.
We knew that was well more time than what we had.
We had trouble with the actuators. We had trouble with the energy problem, the heat problem. We had trouble with the electronics. All these things combined to a story where it just was not going to make it.
It was really, really tough. I didn't sleep, literally didn't sleep for a couple of days. So it was very difficult to, if you will, suck it up and say, we're not going to make this one.
The team gets the bad news just before Christmas. Launch will slip to late 2011.
2 weeks ago, we're excited, we're tired, but we can make it. Then the big bombshell goes off, and we find out that we can't make it.
We'd really like to slip 6 months, but our opportunities don't come like that. We have to slip 26 months.
Some people will lose their jobs as the project regroups for a 2-year delay.
The worst part of this is that we're disbanding our team, at least for a year. And to know that all of those people aren't going to be able to come back, it's going to be some pain along the way. That's what I'm not looking forward to.
It's disappointing. You know, I mean, we'd be launching in a few months. Having that a couple more years out is hard.
"18 months later, JPL gears up for another shot at getting Curiosity off the ground.
On the crane, south slow.
Spacecraft, like children, don't come with instructions.
Stop.
The people who create them have to discover how they work.
3, 2, 1, go. We have motion.
Curiosity has hundreds of parents. They all want to see the first drive.
This rover has only been a rover with wheels for less than a month. And you forget that there is actually quite a lot of pain involved with having a child. I'm feeling a lot more comfortable, but a lot of things can still go wrong. My goal is really to get to the point where I can sleep at night.
Stripped down and bolted to the end of a centrifuge arm, the test rover is about to feel some of the pain of landing day. The sudden deceleration as the spacecraft hits the atmosphere is a wrenching force equal to 15 times the pull of Earth gravity. Enough to cause damage if there are any weak spots in the rover. They'll push it even harder for the test.
How are we looking over there, guys?
All right, moving on up.
Savannah McCoy helped build this rover. Now she has to punish it.
It's kind of intimidating seeing this thing that I've been taking care of basically for the past 2 years. Spinning 80 miles an hour on the centrifuge arm. Oh my God. Any structure has its limit, so we're pushing it right to the line, but you don't want to cross it.
28 minus 2.
Go to 47.
I'm going.
We're at 90%. Come down.
Okay, coming down. Coming down. No, we're okay. Training, everything did good. No, the training's good. I'm just going in neutral.
Oh my God. That was intense.
Very nice.
Touchdown is another shock to the system.
We don't actually know what the surface is going to look like. And so you try to imagine, okay, what's the worst case? And that's what you have to design for.
Computer models say the rover can handle some serious abuse. This says the computer models are right.
You always have this sort of optimistic skepticism as an engineer. You're always hoping that you're out of the woods, but you go to sleep and you don't sleep.
I don't sleep through the night, every night, or any night. Our landing system exercises almost every single piece of the spacecraft. So there are a lot of things that have to be tested to really make sure that this beast that's so very complicated really works on Mars.
Today, they'll test that final unspooling of the rover just before touchdown.
This is the test where we're checking it out. And it is gut-wrenching just from that point of view, because you realize how complicated it is and how much stuff is actually going on.
If we can't do this hanging from a crane in a quiet laboratory here on Earth, we have little right to try to do that.
Hey,
hanging from a set of jets hovering over the surface of Mars. So, if we don't have this right, whatever, we should all go home.
Stand by for test. Test article.
Go.
Safety.
Go.
QA.
Go.
Cameras.
Go.
Rover DAC.
Go.
Descent stage DAC.
Go.
IMU.
Go.
Pyro. We are armed. Test is commencing in 5. 5, 4, 3, 2, 1, fire. Woo! Yeah.
So far, so good.
Yeah, it was. Yeah, it
Not
was.
only with the flight cable bundle, but with the GSE as well.
But it's not over
in
yet.
fact, I checked that with Chris.
After touchdown, the sky crane has to take up the slack in the cables before it disconnects. The cables begin to retract, but one of them, an electrical cable, suddenly stops.
We have a leash, a little spring and a little line that picks up the slack on the umbilical, that electrical cable. And that leash was doing a good job for a while, but stopped picking up the slack. And so you see some of that electrical cable is on top of the rover. And we don't want that because it could have laid over and snagged on something. And when we go to fly the descent stage away, we could be stuck. This, by the way, this is exactly why we do tests like this.
A piece of cord on a $10 spring could sabotage a $2.5 billion mission.
First glimpse of actually seeing the cord through that hole.
Would you just zoom in there just for a second?
If the leash got jammed in the mechanism, it could be a design flaw that would set them back months. But it might be something simpler.
Okay, wait, gentlemen. What's our force margin on Earth here?
Well, this thing is very marginal on retraction force here on Earth.
The spring may not be strong enough to handle the weight of the cable in Earth gravity, where it's twice as heavy as it will be on Mars. That's probably it.
What we can do,
but they have to prove it.
We're in that part of the project which is like the red zone. Our world is full of infinite detail and a lot of paranoia and worry.
You are down 2.0 right now.
We were at 2. Yeah. We did the T15.
They settle on a simple test. From below, they lift the cable to take some of its weight off the spring.
Moving, things moving, it's moving a lot.
It's moving freely, so it's a cable mass issue.
And when you let go, it didn't come down.
The problem is Earth gravity.
Right.
not an issue on Mars.
Okay.
Tom looks like
So,
he's
Savannah,
ready for a bottle and a...
What's involved
In
if
a
we were
pinky?
to...
And I'm ready for a bottle myself.
The scientists have finally settled on Gale Crater as the destination, a basin the size of greater Los Angeles, with a 5,000-meter mountain in the middle. Perhaps once an island in a lake, this stack of layered rocks may tell the story of life and death on Mars. If it lasts long enough, curiosity will read the layers like the pages of a book, from the bottom to the top.
This is a book that's going to have many different chapters. This becomes a mountaineering expedition. This is a place where we could go for 10 years.
Everything will depend on being able to collect rock and soil that might contain evidence of ancient life. It's turned out to be a tougher problem than anyone expected.
It takes 7,000 parts to drill into a rock, extract a sample from the inside of that rock, dump it upside down, divide it into pieces, and then distribute it to the science instruments. This is all stuff that's new, and it's complex. And when new things permeate the entire design, the risk goes up very, very rapidly.
All right, everybody, please.
All right, so again, this is, what we do with the arm is we typically do coordinated motion, right, where we pick a...
Every major system undergoes a thorough risk review to identify the bad things that can happen.
So this is a place where we definitely need the science team, right, to tell us what we should be doing. The baseline...
Why is that not in the list of requirements? Because
I don't give a damn what requirements we wrote down.
There's a lot of gloves off, a lot of critiquing, willingness to engage.
And we're trying, right? We're trying, and you're going to hear that.
I'm not happy at all. And
It's kind of like a war in there. But that's the method for trying to figure out if someone really knows what they're talking about or not.
With launch less than a year away, they're trying to make it work for the first time.
Okay, the inlet cover's opening. Okay, the arm's in position. Brakes are closed, portion door's open.
We deliver to the instrument half an aspirin tablet's worth of soil. Big arm, big turret. And then when all is said and done, it's just this little thing that comes out the end. And it's like, that's it.
It's not much, but it could tell the story of life on Mars. And if it doesn't work, the engineers will have to answer for it.
So we're going to do it 5 more times. Man.
Everybody has invested a lot of time and energy into this. And we're talking about thousands of people. It's a monumental effort making something this big happen. But that's what NASA does. We all want to know, could life have ever existed on Mars? This mission is not going to be easy. It hasn't been easy. But we want an answer, and we're going to go get it.
With 6 months to go, everything moves to Florida and the launch pad.
That was a long day, but there it is. So now the journey really begins.
It's bittersweet in a way. It's really cool to see it, but we kind of realize that we're coming to the end of our lives with the vehicle here on Earth. Take a deep breath.
Oh man, it's been a hell of an experience. The other day I was able to touch the Rover. That was kind of an emotional thing, you know. I'm over there stroking it like a little puppy and had to walk away from it.
The next time anyone sees the Curiosity rover will be in pictures from its own cameras, sent back from Mars. 8 years of work have come down to this: a $2 billion spacecraft sitting on 450,000 kilos of rocket fuel.
On the numbers, launch is pretty scary. You know, they give a 99, 98% probability of success on a launch, which is about what we're giving on our probability of success at landing. So we're going to push the go button, and if things don't go well, we're all in, and our whole investment will be lost. The team wants to deserve success or failure, and that comes at Mars. And so we all have a little bit of butterflies in our stomachs about tomorrow morning.
The planets are aligned. It's time to go to Mars.
NSC, spacecraft to internal power. Roger. Perform launch on time verification.
Roger.
Escort bag. We walked right up to the rocket.
No.
So cool. Good to see
I really want to get going. All through the development, there are tons of challenges that you face that might stop you. But once you light that rocket up, that whole anxiety about should we turn back, should we delay, all of that's gone.
Launch enabled.
There's certitude that on the 5th of August, we get to test our mettle against Mars.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Main engine start, 0, and liftoff.
Wow. It's gone. It is gone.